Welcome back, folks. This is Mr. Johnson with you once again. This is lecture 4.4 on precipitation formation using what we know already about solubility, product, equilibrium, Ksp, and also the common ion effect. I'm going to scroll down my page here and get us started. From page 251 of the textbook, 259 of the ebook, looking at the section here titled Precipitates that form when solutions are mixed together. In the last lecture, we looked about solutions that came from just one solute, what the maximum solubility of a solute can be based on knowing its Ksp or vice versa. In this section, though, we're going to look at solutions that come from two solutes, and specifically precipitation reactions. As it says in blue, when two solutions are mixed, we should be able to predict already which precipitate will form. And I'll remind you of the solubility rules you should memorize. The Ksp value, we should know from the last lecture, represents the maximum product of the ion concentrations in a saturated solution, raised, of course, to their coefficients. If the product of the ion concentrations present exceeds that value, if we find that the product of the ion concentrations is greater than Ksp, those ions will not remain dissolved, and the solution will result in a precipitate. A precipitate will form. It'll be past the saturation point. On the other hand, if the product of the concentration of the ions plugged into Ksp is less than the value for Ksp, that means the solution isn't yet saturated and more solute could be dissolved until a precipitate forms. What this might be sounding like now is a Q versus KEQ scenario. In fact, it is, although it's for solutions, for solubility equilibrium. And so what we call this is a TIP, a trial ion product versus KSP scenario. What we'll be doing is comparing the concentration of ions at a point prior possibly to equilibrium, prior to saturation, and comparing it to the Ksp. If the trial ion product, which is equivalent to Q, is greater than Ksp, then the solution is saturated and a precipitate will form. If the trial ion product, what again is analogous to Q, is less than Ksp, that means the solution is not saturated and a precipitate will not form. If they happen to be equal, then that's when the solution is just at its saturation point and a precipitate hasn't yet formed, but if any more of either ion were added, then that solution would form a precipitate. Let's see how these sample problems look. So I flipped the page looking at sample problem 441 here. The question reads, will a precipitate form when 23 milliliters of a 0.02 molar sodium carbonate solution is added to 12 milliliters of a 0.010 molar magnesium chloride solution? First thing we want to do is write out the reaction and figure out which the precipitate will be. This is going to be a double replacement reaction because both compounds are ionic. And we swap the cations, seeing that on the right-hand side, magnesium pairs with carbonate and sodium pairs with chloride, and when it's balanced, there'll be a 2 in front of sodium chloride. I want to remind you of the 2 at a minimum solubility rules to memorize. If you recollect, all group 1 metal salts, any salt or ionic compound that has an element in the first column of the periodic table will be soluble. Sodium is one of those metals. That's why we know sodium chloride is the soluble product, meaning magnesium carbonate isn't. Because if we're given a double replacement reaction, we expect it will occur and one of the products will be a precipitate. The other solubility rule to memorize is all nitrate-containing ionic compounds or salts are soluble. So if the anion is NO3 nitrate, no matter what the cation is, it will be soluble and the other one won't be. Again, magnesium carbonate we know to be our precipitate, our salt. Once we've identified the solid or the potential precipitate, we write the equilibrium expression for it with its ions when it's saturated. So we see that here in the second row. And because neither of them have a subscript, there's not coefficients in front of either also. We then write the Ksp expression for magnesium carbonate. And from the table in the prior section, we know the Ksp of magnesium carbonate is 6.8 times 10 to the minus 6. So that's our third row here. The next thing we want to do is account for dilution, which I talked about in the last lecture. I want to remind you, to account for dilution, we take the molarity of the original compound, multiply it by its volume that it was delivered in. This is the 23 milliliters, or 0.023 liters of sodium carbonate, and then divide it by the total volume, which is the sum of the 12 and the 23 mils up top, or 0.035 liters. We do that for magnesium chloride as well, and these are the concentrations of the two compounds once they've been added together and once we've accounted for dilution. 0.013 molar for sodium carbonate and 0.0034 molar for magnesium chloride. Meanwhile, because there's only one of each of those ions in those two ionic compounds, there's one carbonate and sodium carbonate, and there's one magnesium ion and magnesium chloride, so will their concentrations be the concentration of the solute above calculated. So these values could be thought of as their initial concentrations, kind of like a Q, except that for solubility equilibrium, we refer to it as TIP, or trial ion product. So we will plug those values into the Ksp expression, or the TIP expression for magnesium carbonate, because remember, they are found the same way, which means we'll multiply the molarity of magnesium ions, 0.013, by carbonate, 0.0034, and we get 4.4 times 10 to the minus 5. We then compare that to the Ksp for magnesium carbonate, and notice that it is greater, because a less negative exponent is in fact greater, and if it's greater, that means that it is past the saturation point, and that in fact a precipitate has and will form. Had they been equal, it would have been right at its saturation point, and had TIP been less than Ksp, it would not have been saturated, and in fact a little bit more of either of those compounds could be added before a precipitate were to form. So I've scrolled down, I'm looking at practice problems 441 here, the problem highlighted in blue. Encourage you to try this one on your own. If you're not quite sure how to do it, look up. You'll use the same steps that are on this page above to solve this problem. And know that you'll need to find the Ksp for lead 2 nitrate on the table that's in section 4.3. Come on back when you're done, see how your solution compares to mine. And as I'm sure you just found out, these are a lot of work. Boy. All right, here's the double replacement reaction. The solid is going to be lead 2 iodate because sodium and nitrate both render sodium nitrate soluble. Here is the equilibrium expression for lead 2 iodate when it's in a saturated solution. Notice there's a 2 in front of the iodate ion because the subscript of 2 is here. I'm then accounting for the dilution effect that happens when these two solutions are combined. There's the molarity, 6.3 times 10 to the minus 2 of lead 2 iodate times its original volume, 0.0085 liters, over the total volume, 1.0085, and that gives me 5.31 times 10 to the minus 4 molarity for lead 2 iodate. And since there's just one lead ion in there, that will also be the concentration we can see down below for the lead ion, which is in the potential precipitate. Same thing for the iodate, multiply it by its original volume, 1 liter, divided by the sum, 1.0085, giving me 1.19 times 10 to the minus 3. And same thing, there's one iodate in that compound, so the concentration of that ion will be the same as sodium iodate, 1.19 times 10 to the minus 3. Here's my TIP/Ksp expression. Remember, they're calculated the same way, but Ksp can only be used when that is a saturated solution. TIP can be any point up to or past that. So it's going to be the lead ion times iodate squared, because there's a subscript of 2 with iodate. So now I'm going to find TIP. I plug in the concentration of lead ions, which is the 531 times 10 to the minus 4. Oops, I'm seeing a mistake over here, folks. That should not be a 3, that should be a 4. And then times 1.19 times 10 to the minus 3 squared. We've got to square the concentration of iodate. That gives me 7.5 times 10 to the minus 10. And if I compare that to the Ksp value on the table in section 4.3, which is 3.7 times 10 to the minus 13, I see that TIP is less than Ksp. That means that the solution is in fact saturated. We've exceeded the maximum ion product that can occur for this substance. So yes, it is saturated, and a precipitate will form under these conditions. Nice work, folks. I'm going to walk you through another sample problem, and the rest of these problems involve the same concepts, same skills, they're just a little bit different. They just bring in some other angles. So, sample problem 442 here on the following page, on page 254 of our textbook. It says, what mass of sodium sulfate is required to start precipitation in 500 milliliters of a 0.03 molar calcium chloride solution? Assuming the volume remains constant, that whatever mass of sodium sulfate is added won't change the total volume to 500 mils. Once again, we write the double replacement reaction between sodium sulfate and calcium chloride. The products are calcium sulfate and sodium chloride. And again, because this is a group 1 metal containing salt, sodium's in there, we know it's soluble, and therefore calcium sulfate must not be. Once again, assume all double replacement reactions occur. So we write the equilibrium expression that exists between calcium sulfate and its ions in a saturated solution, and we write the Ksp expression once again, which is the same way we find the TIP, except that's not going to come into play in this problem. We then say, okay, well, we've got a 0.03 molar calcium chloride solution, and since there's one calcium ion in calcium chloride, that will be the concentration of calcium ions as well. From from this 0.03 molar solution. We know the Ksp of calcium chloride. It's 7.1 times 10 to the minus 5. We know what the concentration of calcium ions will be. Well, what would the concentration of sulfate ions be if it were saturated? And any amount past that would start precipitation. So we're solving for this value because, again, this is the value at which it's saturated, and any amount past that would start precipitation. So we solve for SO4, divide both sides by 0.03, and we get 2.4 times 10 to the minus 3 molarity. Now it asks for the mass of the sodium sulfate, not the molarity. We know that from a molarity and a volume, in this case it's 500 milliliters or 0.5 liters, we can get moles, and we see that the volume times the molarity here gives us moles, liters cancel, and then if you multiply by the molar mass of sodium sulfate, which is 142.1 grams per mole, we get 0.17 grams. So again, here's a case where we knew what the concentration was of one of the ions, we knew the Ksp of the salt, we just needed to figure out what the concentration of the other ion would need to be a saturated solution or to start precipitation, and then we found mass. You probably already noticed, but I misspoke. We were actually on page 253 of our textbook, not 254. But now we're going to go to 254. Don't you worry. I'm going to walk you through another sample problem. It's just a slightly different version of that one, and then we'll give you a chance to solve two practice problems. They're both like the sample problems you've just seen me walk you through. All right, this one says, what is the maximum concentration of sulfate ions that can exist in a saturated solution of calcium carbonate? It's really asking us something similar. The maximum concentration that can exist would also be the concentration that would start precipitation, and if we wanted to take it one step further, we could figure out what the mass of a certain salt is. So similar problem, just 2 steps fewer. Same thing, we've got to write out the equilibrium expression that exists for calcium carbonate with its ions, but because this isn't about another solute being added, we don't have the double replacement reaction also. We then write the Ksp expression, which is the calcium ion times the carbonate ion. And then from the table, of course, in 4.3, we know what the Ksp is for this salt. It's 5 times 10 to the minus 9. Both ions are in a 1-to-1 ratio with each other and with the salt, so they both could be considered X or S. Our book uses S. So if we take the square root of the Ksp, take the square root of 5 times 10 to the minus 9, we get what the concentration of each of those ions would be in a saturated solution, which is 7.1 times 10 to the minus 5. And then in this problem, what we're supposed to know is that calcium sulfate is also a relatively insoluble salt, that the concentration of calcium ions from calcium carbonate could be plugged into the equilibrium expression for calcium sulfate. So we see the equilibrium expression for calcium sulfate here. We find the Ksp for calcium sulfate from, again, the table in 4.3 at 7.1 times 10 to the minus 5. And from the prior problem, we know the concentration of the calcium ions due to the calcium carbonate's Ksp is 7.1 times 10 to the minus 5. And if we then solve for sulfate, sulfate could exist at a 1 molar concentration when the solution is saturated. All right, so we're going to give you a shot at practice problem 1 in this section called practice problems 442 here. The question in green asks you to calculate the maximum concentration of strontium ions that can exist in a solution of 0.05 molar sodium fluoride. This is a little different than the one above. In fact, it's a little bit easier because we're not being asked to calculate the concentration in a saturated solution, where above we had to use the Ksp and solve for what the concentration of that ion would be. We're given it, in fact. So we know the concentration of sodium fluoride. If we know what the concentration of fluoride is in sodium fluoride, then we can plug that in to the Ksp expression for strontium fluoride, because it's ultimately strontium fluoride we're looking at here that is a slightly or fairly insoluble salt. Give this one a shot, come back, see how your answer compares to mine. All right, so sodium fluoride is at a concentration of 0.05 molar, and remembering that sodium is a group 1 metal, it's completely soluble, so the concentration of sodium fluoride will be the concentration of sodium ions because it completely dissociates into its ions. So will it be the concentration of fluoride ions because it's 1-to-1. And that's the ion that is going to show up in the equilibrium expression below for strontium fluoride. Strontium fluoride is SrF2. So we've got strontium 2 plus ions here and 2 fluoride 1 minus ions here. The Ksp for that is the concentration of strontium times fluoride squared. If we substitute in for the Ksp, what we get from the table, 4.3 times 10 to the minus 9. and for the fluoride ions concentration from above at 0.045 squared, and sulfur strontium, we get 2.1 times 10 to the minus 6 molar. So that's the maximum concentration of strontium ions that could exist in a 0.045 molar sodium fluoride solution. Past that, they're going to precipitate. They won't be dissolved at all. All right, here's another problem to try. It's on the same page here. It's problem 2 in pink. Give this one a shot. This is like the first sample problem I did just a bit ago. So if you need to look back at that for how to do it, do so. Give this one a shot on your own, please. Come back and see how your answer compares to mine.
All right, so behind this problem, we're supposed to note the sodium carbonate will dissociate completely into its ions, and that it's the carbonate from the sodium carbonate that can form a precipitate with magnesium carbonate. Magnesium carbonate is not very soluble. It's on that table, of course, in 4.3. So we've got the equilibrium expression for magnesium carbonate in a saturated solution. I've written the Ksp expression for magnesium carbonate, and I've set it equal to its Ksp. Meanwhile, if we know that the concentration of magnesium ions in this solution is 3.2 times 10 to the minus 3 molar, we can solve for what the concentration of carbonate ions would need to be for the saturation point to occur, / for precipitation to begin, or in this problem, to begin to soften the water. It's the same thing here, same kind of problem. All right, that comes out to 2.3 times 10 to the minus 3 molar. Solving for the concentration of carbonate gave me 2.13 again times 10 to the minus 3 molar. Well, that's moles of carbonate per liter. We need to acknowledge, though, that there's one carbonate ion in a sodium carbonate ion. So I put that here in dA. Don't have to have that step there, but it had it been a sodium ion, for example, it would have been a 2-to-1 ratio. So in this case, it's 1-to-1, and then multiplying by the molar mass of sodium carbonate in the end, 105.99, gives me 2.2 grams of sodium carbonate needed to give us the concentration of carbonate ions that would put this solution at its saturation point / begin precipitation / begin to soften the water. All the same thing once again. All right, we're down to the last section of this video called the common ion effect, and we're looking at page 255 of our textbook or 263 of our ebook. The statement in green reminds us that the solubility of a substance depends on the temperature. I skipped a segment of that sentence. We know that. The greater the temperature, typically the greater the solubility, but it depends on if the dissociation reaction is exo or endothermic. We know that KSPs, KEQs are temperature dependent. But the solubility of a substance will also depend on the presence of other ions in the solution. And it will only depend on if the other ions in the solution are ions in common with the salt whose solubility it is we're contemplating. So here's the equilibrium expression for silver carbonate. If there were silver ions present already in water, that would affect the solubility of silver carbonate. So too, if there were carbonate ions already present in water, that would affect the solubility of silver carbonate. We know from Le Chatelier's principle that things will shift equilibrium. If there's silver ions present already, that is going to shift the equilibrium to the left and cause silver carbonate to be less soluble. Same is true of if there were carbonate ions present in solution already. If we, per se, increase the concentration of carbonate ions by them being present already, that would shift the equilibrium to the left, and that would decrease the solubility of silver carbonate. The key here is that if there are ions in common with a compound we are contemplating the solubility of, that will decrease the solubility because, as we just saw, it'll shift it left. Meanwhile, if there were some way to remove either of these ions, silver ions or carbonate ions, which in fact there are, that would increase the solubility of silver carbonate because it would essentially decrease the concentration of the product, causing the equilibrium to shift to the right. So again, ions that are in common with one of the two ions of a salt whose solubility is we are contemplating will decrease its solubility, and we're going to learn mathematically how and why. I flipped the page. I'm on 256 of the textbook, 264 of the ebook, looking at the section here titled Calculating Solubility with a Common Ion Present. And again, it reminds us in the pinky purple, the presence of a common ion in the solvent decreases the solubility of the solute. And we're going to look at, through a sample problem here, the solubility of magnesium hydroxide in water when there isn't any common ion present, when there isn't either magnesium ion already in the water or hydroxide ion, and compare it to its solubility in magnesium chloride, realizing that the magnesium ion is common with magnesium hydroxide. And here it is. What is the solubility of magnesium hydroxide first in water with no common ion present, and then in magnesium chloride at a concentration of 0.1 molar? First step, as you might imagine, is to write out the dissociation or equilibrium expression for magnesium hydroxide when it's in a saturated solution. 1 magnesium ion, 2 hydroxide ions, acknowledging again that magnesium, if it is S, means hydroxide will be 2S. There's the Ksp expression for that equilibrium expression. Magnesium's concentration to no exponent, hydroxides to an exponent of 2, given the coefficient of 2. We then set that equal to the Ksp for magnesium hydroxide, which again is obtained from the table in section 4.3. And that's 5.6 times 10 to the minus 12. We substitute in for magnesium S and for hydroxide 2S, because remember, when you square 2S, it's really 4S squared times another S is 4S cubed. So if you divide 5.6 times 10 to the minus 12 by 4 first, and then take the cube root of it, we get the value for S, which is the concentration of magnesium. But that's also the molar solubility, because for every magnesium, there was 1 magnesium hydroxide. So again, S represents the molar solubility of magnesium hydroxide. And that's the answer to part A. In the presence of water, in the presence of no common ion, the molar solubility is 1.1 times 10 to the minus 4. Only 1.1 times 10 to the minus 4 moles of magnesium hydroxide would be able to dissolve in a single liter of pure water. For B, we wouldn't really need to write the equilibrium expression again, but it is written again, same as it was above. But now that there's a common ion present, we need to set up an ice table, an ice diagram. And that is true for all of the problems that involve common ion. Because initially, there is now already a concentration of magnesium ions present from the magnesium chloride. Normally there isn't. Initially, all there is solid. Again, now, with the common ion present, the initial concentration of magnesium is 0.1. And that comes from the 0.1 molar magnesium chloride. Because there's just 1 magnesium per magnesium chloride, it was 0.1. If this were chloride, though, whose initial concentration it is, we were plugging into this table, it would be 0.2, because there's 2 chlorides. Meanwhile, there's no initial concentration of hydroxide. There's no other substance already dissolved in the water with hydroxide in it. Magnesium hydroxide, we know we leave blank because it's a solid. Magnesium goes up by X, and hydroxide goes up by 2X. And that means at equilibrium, magnesium's concentration will be 0.1 plus X. In prior problems, it was just X. But now, with the initial concentration of 0.1 added to X, we get 0.1 plus X. And hydroxide is just 2X. All right, something important's coming your way. For the first time ever in this problem, written here in step 3, is a mathematical shortcut that can be taken in a problem like this, or in acid-base equilibrium problems, which we're going to be solving a lot of in the next few weeks. If we appreciate that Ksp is a pretty small value, it was 5.6 times 10 to the minus 12. That means that there's very little dissociation of the magnesium hydroxide. It means the concentration of magnesium and hydroxide at equilibrium will be quite low. If we add a very small number, x, to 0.10, the contribution that x makes to 0.10 is insignificant. In fact, in terms of sig figs, it wouldn't even show up. So in this case, appreciating that x is very small, and that adding it to 0.1 won't really make a difference to the value of 0.1, we can ignore x in the equilibrium concentration for magnesium. And notice down below, that has happened. Instead of 0.1 plus x here, we just see 0.1. You could have kept it at 0.1 plus x and solved this, but it becomes more difficult and requires the use of a quadratic, which in this class you aren't expected to have to use. So take the shortcut. 0.1 plus x is, for all intents and purposes, 0.1. Hydroxide is still 2x, so that becomes 4x squared. And when we solve for x in the end, which is the concentration of magnesium ions, and once again, the molar solubility of magnesium hydroxide, we see that it's 3.7 times 10 to the minus 6. And as we might expect, that value is lesser than it was for pure water's molar concentration or molar solubility of 10 to the minus 4. So in fact, the presence of a common ion reduces the molar solubility of magnesium hydroxide. All right, one more problem to do. We're on the same page, just scroll down looking at practice problem 443 here, highlighted in blue. calculate the molar solubility of silver iodate in a 0.1 sodium iodate solution. So it is the iodate that will be the common ion with silver iodate, and this problem will solve very similar to the one above. Give this one a shot, set up your ice table, take that mathematical shortcut, see how your answer compares to mine. Have fun solving this. First thing I did is wrote the dissociation expression for sodium iodate that we are given a concentration of 0.12 molar for, and I used a rightward pointing arrow. Again, sodium is a group 1 metal. It means it's completely soluble, so it won't be in equilibrium with its ions. We can expect all of it will become dissociated ion. And with just one sodium per sodium iodate, the concentration of sodium will be 0.12 molar, as well iodate's concentration in this solution will be 0.12 molar. And we see that showing up over here in our ice table. I've then written the equilibrium expression for silver iodate. 1 silver ion, 1 iodate ion per silver iodate that is dissolved. That should be an S there, I'm appreciating. It should be a solid. So pretend that that's an S. Ksp expression is here. Silver times iodate concentration is equal to Ksp. And then I go over here to my ice table. I leave silver iodate out of it because it's a solid. It doesn't show up in the Ksp expression. The concentration of silver ions is 0 to begin with. There's no silver in the solution, but there is 0.12 molar iodate. They both go up by X, and again, appreciating that the Ksp for this salt is extremely low, 10 to the minus 8. The value for X will be very small, and when added to 0.12 is so negligible that we can assume the concentration of iodate will be 0.12 at equilibrium. So we plug these two values into our Ksp expression, X for silver, 0.12 for iodate, and when we solve for X, we get 2.7 times 10 to the minus 7 molar. That is the concentration of silver ions when this solution is in equilibrium with its solid. And it's also the molar solubility because there's 1 silver per silver iodate. So that's our final answer. Nice work, folks. Congratulations for making it to the end of this lecture. Good luck with your review questions. Look forward to seeing you soon.